So, welcome to the last module of this course, where we will be discussing molecular dynamics simulations, and in this part we will be talking about classical molecular dynamics. There can also be quantum molecular dynamics. So, in classical molecular dynamics simulations, we are doing nothing more than integrating Newton's equations of motions for a large number of interacting particles. So, basically there are particles, they are moving around in space and you are following the position coordinates and the velocity coordinates of the particles. The physics of the problem is decided, I mean what you want to study, the physics of the problem is decided by the interaction potential. So, depending upon what physics you are studying, you choose different expressions of the interaction potential. So, if you are doing Newton's equation of motion, it is nothing but solving m d2 r dt2 equal to minus grad of v, v being the interaction potential. You choose different potentials depending upon the physics of the problem, and on solving this second order differential equation, you essentially get positions and velocities, or positions or momenta as a function of time. Here I is the particle index. Of course, you are not looking at just one particle, but you have a bunch of particles interacting with each other, right. So, in molecular dynamics simulations, you are essentially looking at the time evolution of a system of particles, and if you are doing statistical physics, then once equilibrium is reached, you can take the statistical time average. So, here you are basically taking time average in molecular dynamics simulations. In Monte Carlo simulations, the Ising model which we discussed previously, you are taking the ensemble average. The system was going from one microstate to the other, different copies of the ensemble. Here also the system is going, if the system is in equilibrium, the system is going from one microstate to the other, but as a function of time. So, when you take a statistical average, you are essentially taking a time average of the system. However, in molecular dynamics, one can also study the time evolution of a non-equilibrium system. Suppose your initial coordinates, the positions and the velocities of the system of particles, they are not in equilibrium, they are in some special initial condition. Then you can also study how the system is moving towards equilibrium, especially since you have access to positions and velocities of all the particles, and you are doing a classical simulation, just integrating Newton's equation of motion, right. So, what would be the picture? What you will have is a simulation box with PBC, PBC being periodic boundary condition. So, here you have a box blue colored, right, and within that you have many particles which are basically moving around in space. So, I have labeled 1, 2, 3, and here you have I, and you could I plus 1. In general, you could have n particles in a box of volume V. You can take a cubic box, you can also take a spherical box, and so on and so forth. But here we have periodic boundary condition. Remember, you can also have a box with walls. So, you can have also a confined system, and you see how the particles are moving around due to interaction with each other, as well as when they reach the wall, they could collide with the wall and come back into the system, right. So, basically you are trying to model nature with the appropriate potential, and so you have n particles in a volume of box V, and you could also basically fixed, you will typically be looking at the system at a fixed temperature. You can also change temperature, there is no problem. If you want to look at a system at different temperatures, then you also can change the temperature. How do you decide, how do you measure the temperature? It is by equipartition theorem, which holds in equilibrium, where half mvi square for a particle equal to half kBt. So, this is for every degree of freedom, right. So, this would be like Vx square, half mvx square, in half mvx square expectation value, average value equal to half kBt. and that is what the equipartition theorem says. In general, if you have n particles and if you are in 3D and you have 3n degrees of freedom, so then 3n mv square over all the particles. So, basically you are calculating the total kinetic energy of all the particles, and expectation value of that will be equal to 3/2 n kBt. Here the Hamiltonian is of the form pi square by 2m summation I equal to 1 to 3n. So, basically half, I mean pi square by 2m is also nothing but half mv square. So, you have half m vx square plus vy square plus vz square. It is every degree of freedom. So, basically if I was the particle index, then I would run from 1 to n. However, this I corresponds here to the degree of freedom. So, in 3-dimensional space you have the x is 1 degree of freedom, y is another degree of freedom, z is another degree of freedom, and if you have n particles, I runs from 1 to 3n, and this is the potential term. Now, for equipartition theorem, you might know that only terms which are quadratic in the Hamiltonian, like pi square by 2m is quadratic in the Hamiltonian. So, only if you have terms in the Hamiltonian where it is appears as a whole square, pi being the momentum whole square kinetic energy, only then does the equipartition theorem hold. So, you cannot say that half of potential energy, average potential energy is related to half kBt, I mean per degree of freedom, right. So, here we have considered a potential which is basically dependent upon the position of two particles, but in general you can have potential which is a 3-body interaction, 4-body interaction. It can depend, if it is a 3-body interaction, it will depend upon Ri, Rj, Rk, these are basically the position index of 3 different particles. It could also depend upon theta. You could have a theta dependent potential, you could have a where theta is essentially the angle. So, between vectors. So, suppose that this is a particle, this is a particle, this is a particle, and suppose they are connected like this. So, this is I, say this is j, and suppose this is k, and then basically r I minus r j. So, you will basically have this vector, and then you will have another vector like this. So, if you have a 3-body interaction, the potential will depend upon all the relative values of r I and r j, and also on theta. It could, I mean, so it depends, as I told you, the form of the potential depends upon the physics of the problem, right. And you could have also have torsion terms if need be, I mean angle dependent potentials, as I said. So, in this course we will be basically looking at a canonical ensemble where we are fixing n, v and t. So, number of particles fixed, volume fixed and temperature fixed, but you could also look at constant pressure simulation. So, when you fix a pressure, so then you would basically look at the NPT simulation, number of particle fixed, pressure fixed, which means volume can fluctuate, and the instantaneous volume can fluctuate. Of course, you will have an average volume, and you fix the temperature. Of course, each of these coordinates can also be changed, but then you are changing the not the system, not the interaction, but you are taking the system at a higher temperature or a higher pressure, or if you are changing V, keeping n constant, then you are changing the density of the system, and so on and so forth, right. So, we will be considering NVT, but you can also do NPT simulations, molecular dynamic simulations. As I told you, particles move around as per the interaction potential. The potential determines whether there is an attraction between them, then particles will come close together, and depending upon the density, number of particles by volume, temperature, pressure, one could identify whether the set of interacting particles is a liquid, a gas, a solid. There could be many other phases, depends upon, again, I mean, there could be the nematic phase, there could be a complex crystalline phase, and so on and so forth. So, as I told you, the molecular dynamics simulation, the physics of the problem is decided by the potential. You could even, using molecular dynamics simulations, look at how Neptune is going around the sun. But if you are looking at Neptune, then we are basically looking at the Newton's gravitational law, gmm by r square, and of course, Neptune or whatever planet or whatever you are interested to look at, it would be affected by not only the sun, but by the earth, Jupiter, Saturn, and so on and so forth, Pluto, asteroid belt, and so on and so forth. So, if you were looking at gravitational potential, you would have the 1 by r square. If you are looking at a charge system, you will be looking at the Coulomb interaction, this is 1 by r. So, gravitational potential, Coulomb interactions, these are typically long range interactions, they really act as 1 by r, and this 1 by r fall off can be felt over very large distances, right. But in principle, you can do molecular dynamic simulation with that, but the calculation of long range forces is slightly more complicated. You have to calculate part of the force in Fourier space and some in real space, and so on and so forth. So, we will be mainly concerned with short range forces. The calculation method will remain the same. If you have interactions like this, calculation of force becomes slightly more complicated, but rest of the algorithm remains the same. If you are doing a molecular dynamic simulations with short range forces, it's slightly simpler than dealing with long range forces. Since you are just learning the principle of molecular dynamics and you will calculate some quantities, we will take the simpler problem of a problem with short range forces. Having said this, what does actually molecular dynamics simulations entail? Going to a slightly more detail than what I have been discussing up till now. Basically, you will have n particles. So, you initialize the position of and velocity of n particles, right. Now, if you have a potential, then if you know the position of the particles, you can calculate the force acting on each particle. Once you know the force and you already have the velocity, because you have initialized it, you can update the position and the velocities of the particles. So, you have the new positions and the new velocities of the particles, Newton's law, that is what Newton's law tells you. And once you have the new positions, you can calculate the new force, right. So, you have access to the new force. Moreover, you should collect data to calculate your relevant statistical quantities, right, because the particles are going to move. Basically, if you are looking at the statistical averages, you could be identifying a phase, you could be identifying the dynamics, and that is all that is there in molecular dynamics simulation. Just 3 steps: initialize position, calculate force, update position and velocities, calculate new force, with that update the position and velocities, and with that calculate new force, and do this n iteration time. So, then you basically get a trajectory of all the particles in space. At the end of your simulations, after n iteration simulations, how many iterations to choose? Of course, those are details, we shall come to it when we actually implement it, implement the code. So, at the end of the simulation, you analyze the physics using either stat phase, or if you are doing suppose some solving the Newton's equation for suppose the planets in the solar system. So, you can do it, you want the trajectory, you could use astronomy, you can look at interaction between galaxies. Again, as I said, I mean, what you want to do with it, what potential you use, whether it be galaxy is your unit, or planet, or smaller particles, nanoparticles, or interacting liquids, that is decided by or the physics decides the V of r, but the molecular dynamics simulations just tells you how to integrate Newton's equation of motion efficiently and in a reliable manner, right. That is all that is there to it actually, but you will see, though it sounds so simple, there are complications which you will have to be aware of. If you just do it naively, you will get soon get infinities, your simulation is not going to work. So, the reasons molecular dynamics simulations is being taught at the end of the course is because there is a lot of scope for error. It is more complicated than any of the things that you have learned before. In principle, it is simple, it is just you have to be a bit more careful about various aspects. We will come to it as we go along the course. So, message, we are essentially solving 3n differential equations for position, 3n differential equations for velocity in molecular dynamics, and keep calculating force, and with this new force keep updating these quantities, right. So, that is all that is there. Now, updating the expression for the position and velocity of the particles, right. This is a relatively very easy step. All that one has to do is calculate a suitably small value of delta t. The delta t basically here you are discretizing time, right. When you solve the differential equation continuously in your analytic course, so then time is nearly continuous, delta t goes to 0, but here you want to take a finite, you have to take a finite, you are discretizing time and saying okay, I am looking at the positions at time t1, at time t2, at time t3, t2 minus t1 is constant, t3 minus t2 is constant, and so on and so forth. And dt, the value of dt or delta t has to be small enough that the Newton's equations are integrated correctly, and of course, we will check whether they are being integrated correctly or not. But though delta t has to be small enough, if you want to look at a very long trajectory, you also want it to be large enough. I mean, you really do not want to look at take the smallest possible delta t, you want to take the largest possible permissible delta t, which allows you to integrate Newton's equation of motion correctly, right. If you have a too large a delta t, then your Newton's equation will not be calculated correctly, it will not be updated correctly, you will not get the right solution to the Newton's equation of motion interacting by a potential. If you take very small delta t, then to have a large trajectory, you will have an extremely long number of iterations, you will have to wait for days for the simulation to complete. So, you want to really take a small enough delta t, but large is permissible, right. So, that your simulation runs quickly and you can get your you can sit down to analyze your physics results. What I was saying is the calculation of positions and velocities, update of this, there is a relatively very cheap and computationally cheap process, it is a easy process. However, calculating the force is relatively difficult and computationally expensive. And why is that? Because you have to calculate the force for between a particle and all other n particles, because in practice the interaction could go to infinity, right. Of course, there are steps to handle this aspect, you especially for short range forces, you do not want an n cross n calculation, you want to reduce it, we will discuss that. But in principle, here for each calculation of force, you have to calculate the force between each pair of particles, which is a n cross n process, and then you have to calculate the distance and the expression, whereas this part, if you have n particles, you have n steps, or rather 3n steps to update position and update velocity, right. So, so large part, when I say that we will be discussing molecular dynamic simulation, a large part of the discussion will actually be about this aspect and not this aspect. This is trivial, as you shall see. At the beginning, at the introduction, even before I go get down to the details, let me tell you what molecular dynamics simulations gives. You know, you have position and velocity at each instant in time, but you can also study a system with a so called off lattice Monte Carlo simulations. We did a lattice Monte Carlo simulations in the Ising model, right, in the previous module of the course. But you could also look at a system of interacting particles by Monte Carlo simulations. And if you have potentials and particles can move around in space, you can have an off lattice Monte Carlo simulations as well. So, let me compare what advantages you have with Monte Carlo simulations, what advantages you have with molecular dynamics simulations, when should one do a molecular dynamics simulations and not be happy enough with a off lattice Monte Carlo simulations. Typically, Monte Carlo simulations are much faster than molecular dynamics simulations, but before I compare, I have to briefly tell you what is an off lattice Monte Carlo simulation, right. Only then can you compare, only then can I compare, and only then can you take a judicious decision whether you want to do you want to study a system by Monte Carlo or by molecular dynamics. So, what one does in a Monte Carlo simulation is one takes a box, just like in molecular dynamics, and these red dots are essentially a large number of particles which are distributed in space. So, if for each you have an x coordinate, no v coordinate, no velocities in Monte Carlo simulations. So, what you have is the x coordinate of each of these particles, right, and in space is continuous. So, the particles can occupy any point in space. It is not that they have to occupy certain discrete point in space. If that is true, then you would call that essentially a lattice. So, here particles can move around in space, even if they are sitting in a lattice. If we are looking at a crystal, they might be sitting on a lattice, but they might be jiggling around due to thermal energy, right. So, then space is again continuous. I mean, they can move in continuous space about its average lattice position. That is what atoms do, right, I mean in a crystal. And in a liquid or in a gas, basically they move all around the space. I mean, it is not that they can occupy only discrete points on a lattice and move around that, right. So, coming back to Monte Carlo simulations, these particles are basically occupying different points in space, they are not overlapping. And to perform a Monte Carlo simulation, what one does is randomly choose a particle. In Ising model, we were choosing randomly choosing a spin in the lattice. Here, we are just randomly choosing a particle using a random number generator. If we want to give it a displacement, so in Ising model we were giving a flip. So, if the spin was pointing up, we were giving a flip. We are basically changing the giving the spins a flip, we were changing the microstate of the system, and then we would decide whether we would accept or reject the trial spin flip. Here, what we are going to do is give a displacement in a random direction to particle I, right. So, we will give a trial displacement of particle I in a random direction by this delta r I. But before we give the random displacement, we calculate the initial energy of the system, right, just like we calculated the initial energy in the Ising model case. Then after giving a random displacement, so suppose this particle would have moved somewhere here. So, that would change that would result in a change of the interaction between this particle and the other particles, a change in the potential energy of the system. And so, we calculate E f, the new energy after the displacement. trial displacement. Now, just as in the Ising model, if delta E, if the change in energy is less than 0, if the energy decreases, then we accept the move, else we accept this trial displacement move with probability e to the power minus delta E by kBt. If delta E is positive, then we accept it with probability e to the power minus delta E by kBt. And if we repeat this choosing a particle n times, where n is the total number of particles in the system, then you say that you have done one Monte Carlo step, right. So, basically you choose a random particle, try to move it, choose another random particle or choose another particle randomly, try to move it, and you do this n times, and you have essentially generated a different microstate with a different position of particles, a different value of the energy, and whether high energy microstates will be accessed or not will depend upon the statistical physics. This is of course only in equilibrium, and if you repeat this n MCS times, you would have basically generated so many different microstates of the system, and you can calculate your statistical averages. Note, while we were discussing all of this, never once have I been mentioning the word velocity, never mentioned the word kinetic energy. It is just a position based. You are changing the position. What is the change in energy? Whether the new microstate will be accessed or not with probability e to the power delta E by kBt, or rather e to the power minus beta E I, I being the energy of the microstate by the partition function. Right? This is the important sampling. But in all of this, there is no mention of velocity. It is just a position based. So, in Monte Carlo simulation, the degree of freedom which you have, which you are working with to different microstates, be different microstates of the ensemble, is xit, whereas in molecular dynamics simulations, which I denote by MD, molecular dynamics, and Monte Carlo is MC, Monte Carlo, you have in molecular dynamics you have access to both position and velocities. So, this is the key difference. So, if you want the exact trajectory of a spaceship in space, you do molecular dynamics. The interaction might be the same 1 by r, but you can't do a Monte Carlo, because there you are trying out random moves. If you want the exact trajectory of Neptune or a spaceship or some galaxy, then you do molecular dynamics. Even when you are looking at suppose solid, liquid, gas, where you are interested in statistical properties of the system and not an astronomical system, say, then where if you need to understand the physics of your system the velocity degree of freedom, then you can't do a Monte Carlo, because Monte Carlo has only positions, right. Now, suppose you want to calculate the velocity profile of a fluid in shear flow or say in Poisson flow, then you have to do a molecular dynamics. Though Monte Carlo, as I told you, is faster, it gives you statistical properties faster, but if you want some dynamical properties or you want to look at approach from a non-equilibrium system to a equilibrium system, how the system is relaxing, then you would typically do a molecular dynamics simulations. Having said that, let me tell you, though we will not discuss it in great detail, one also at times looks at Monte Carlo simulations to look at dynamics or evolution of a system, that is also done, but you do not have access to the velocity degree of freedom, right. So, this has been a general introduction to what and when should we use molecular dynamics, what is the basic ideas of molecular dynamics. Now, slowly let me enter a more gory detail. Okay. As I told you, there is the update of positions and velocities, and this is the calculation of force, right. The simple part is update of velocities and position, and whereas one can also use the Runge-Kutta method, which was discussed in the differential equation module. what we will discuss in this module is another method, is the so called Whirl algorithm. Okay. One can also use the Runge-Kutta, but we will discuss the Whirl algorithm, and the Whirl algorithm has the advantage that the equations of motion that we use to update or to calculate Newton's equation of motion, the trajectory of the particles, they are time reversible. So, that is implicitly there. I mean, the way this Whirl algorithm, or the update of position and velocity, is arranged. So, in the Whirl algorithm, all that we are using is nothing more than the Taylor series, the Taylor series expansion. Suppose you have the access to the position and velocity of all the particles. You have initialized the velocity and position of all the particles at time t. Okay. Then you can calculate well, if you have the position, you have also calculated the force. From force you get the acceleration. Then using Taylor series, you can write down the position of particle I at time t plus delta t using x I t. So, you need to know the position of the particle at time t plus dx dt, right. That is what the Taylor series expansion says, calculated at time t into delta t plus half d2x dt2 double derivative calculated at time t. So, this is nothing but the acceleration. Acceleration can be calculated from the force into delta t whole square plus higher order terms, right. Similarly, you can write x I at t minus delta t at time previous as x I t. You are doing just a Taylor series expansion, nothing more than that, but of course, this thing is nothing but the velocity, this thing is nothing but the acceleration, and if you have x t minus delta t, the only difference that you get is you have a negative sign here instead of a positive sign. The other terms remain the same. Now, if you add this equation and this equation, right, if you add these two equations, then you essentially get x t plus delta t, the position of particle I at time t plus delta t. You get 2 x I calculated at time t, acceleration at time t into delta t whole square, and basically if you added, I bring this term to the right hand side of the equation. So, this is your expression. So, using Taylor series, if you want the position of time at t plus delta t, you need the position at time t, the position at time t, right, the acceleration at time t. Moreover, you need the position at time t minus delta t, right. So, 2 steps back. So, this is how you would calculate it. If you subtract this equation from this equation, then you would get x t plus delta t. So, here you would get x t plus delta t minus x t minus delta t. So, which is subtracting, and then these terms would cancel, and what you would have is dx dt I have written as velocity intentionally, because that is what it is, calculated at time t into delta t. So, here basically you have just managed to calculate V I at time t, right. So, here you have position and which depends upon x t plus delta t, and here you can calculate the velocity at any time. But then what you need is the position at time t plus delta t and the position at t time t minus delta t. So, you need these two positions at two different times to be able to calculate this in general. Now, doing a bit of algebra and some mathematical jugglery, you can also write Whirl algorithm into the velocity Whirl algorithm is just a bit more algebra than that. And in the velocity Whirl algorithm, what you do is x t plus delta t, and Whirl and velocity Whirl are absolutely equivalent. You can even use this, or you can use the Whirl algorithm. I have a bias towards the velocity Whirl algorithm because I use it, but there is nothing holy about it. You can use either of them. So, the velocity Whirl algorithm, what you do is x t plus delta t equal to x t plus v t into delta t plus half a t delta t whole square. So, you see that this is at time t, this is at time t, this is at time t, right, and then you get the position at time t plus delta t, and the velocity can be written as velocity at time plus delta t can be written as the velocity as time t. So, the previous time, the force, or rather I should write the acceleration, f t by m is acceleration. So, the acceleration at time t and the acceleration at time t plus delta t. So, you see here again, to calculate the velocity at time t plus delta t, you need the force at two different times, including the force at time t plus delta t, right. In the previous case, to calculate velocity, you are needing the position at time t minus delta t. Same here, to calculate the position, the new position of the particle after time t, you are needing the position of the particle at t minus delta t, whereas this has simplified a bit, and here all you need to update the position is the position, velocity and acceleration at time t. However, to calculate the velocity at time t plus delta t, you need the force or the acceleration at the previous time, as well as the acceleration at the current instant in time at time t plus delta t. So, in the Whirl algorithm, you have to update the position first using this equation. Once you have x t plus delta t, you can calculate f t plus delta t, right, because you have the new position with the new positions you can calculate the new forces. Save the old force in some other array. So, you have to update the force, save the old force, and with these new two forces update velocity, and that is all that is there to molecular dynamics. Repeat. So, you basically, if you keep on doing this, you have the position, the new position, the new force and the new velocity. So, with that you can calculate the position at time t plus 2 delta t, then you calculate the force at time t plus 2 delta t, and then you calculate the velocity at time t plus 2 delta t. You have access to these three, immediately you can go to this step and calculate the position at t plus 3 delta t. So, what are you getting? You are getting position, velocity and force at incremental values of time. You are getting essentially the trajectory in space, x as a function of t as t changes, as the particles move around, as time progresses. You have the velocity of particles as time progresses, as t 1, t 2, t 3, t 4, t 3 being greater than t 2, t 2 being greater than t 1, right. So, that is all that is there in the update of position and velocity. However, you will see that the calculation, the force calculation step will take much more time.